You've probably noticed something along our journey here through physics until now. Very rarely are we solving for things directly. Instead, almost always, we are tracking how systems change through time or through space or depending on other factors. Think about the velocity of a point on a celestial sphere as it rotates about its own axis through space. It changes as we move away from the equator to the poles, where it effectively becomes zero, thus depending on the sphere's latitude. The propagation of a radial wave depends on both space and time. The field of a magnetic dipole varies intricately with position. In the mathematical sense, you would recognize these as well as many physical quantities we've acquainted ourselves with as functions. And all of these functions undergo changes like the energy stored in a capacitor over time, or the velocity of an object at any instant while undergoing projectile motion, or the refractive index as one moves along a grating. To truly understand how such systems actually work, it becomes necessary to ask how they evolve in response to underlying factors, the question about rates of change. And that is the exact question we seek to address today in our study of differential calculus to see how it plays into physics. Our study of differential calculus starts with grasping the concept of derivatives. To understand that, let's take a look at this graph. Say you have this function f of x equals x squared. Now, if we take any 2 points on this graph, one at x and the other at, say, x plus h, then the output of the function at these 2 points would be x squared and x plus h whole squared, respectively. If you look at the secant line joining those 2 points on the curve, you see that it reflects the average rate of change across the interval. Now, what we want to know is the rate at which the function changes when h is infinitesimally small. So as we keep shrinking h such that the 2 points get closer and closer, we end up with what we call the derivative, that is, the instantaneous rate of change of a function at a point. Mathematically, this is defined as f prime of x, or df by dx, which is the ratio of the differences in output to the tiny change in x, which is delta x, or h, as it tends to 0. This limit captures how sensitively the function responds to changes in its input, and this is exactly what aids us in physics when we ask how fast is something changing right now. Let us take a real-life example. Take a long-haul flight across the globe, say from California to India, with a stop in between. As the plane accelerates, cruises, lands, and then takes off again, the total distance flown over time forms a continuous function. The average speed over an interval is the slope of the secant, but the real interest lies in the instantaneous velocity, v of t or ds over dt, which is what the speedometer reads at that exact moment. That's what the tangent, or the derivative, provides us with. Consider another example, a ball thrown straight up. Its height over time forms a clean parabola. The slope starts high, it's rising fast, then slows to 0 at the top and flips negative as it falls. The derivative here gives the vertical velocity. Again, the secant shows the average behavior, but the tangent tells us what's happening at any instant, giving us the vertical velocity of the ball as a function of time. Thus, derivatives, as you see, are fundamental in physics, allowing us to go from observing change to quantifying it in a precise manner. So now that the concept is clear, we should take a look at some commonly used derivatives which can come in handy while solving problems. For exams, of course, you need to memorize them, but here we'll try and build everything from scratch so you truly get a feel and understanding of the functions, which can make the memorization and recall process easier in turn. Let's go back to the function x squared and see what happens to it. To visualize the derivative, let's draw a square with side x. Now, what happens to the area if we increase x by a tiny amount dx? You can pause and ponder on your own if you wish to for some time. Okay, so here's how the square grows. A vertical strip on the right of area x times dx, a horizontal strip below of the same area, and a tiny square in the bottom right corner of area dx squared. So the new area is the original area x squared plus 2 times x dx plus dx squared. We can ignore this last bit since dx, as we know, is super tiny, so dx squared is even tinier, negligible in comparison. So what remains is x squared plus 2x dx, meaning the change in area delta A is approximately 2 times x dx. Divide this by x and you get the derivative of x squared as 2x. So visually, the derivative represents the area gained for increase in x, and this process gives it to us naturally. Let's try to do the same thing with a cube. The volume of a cube of side x is x cubed. Again, increase x by a tiny amount dx. What's the new volume now? The cube now grows by 3 large slabs, each of volume x squared times dx along the 3 outer faces, and then there are 3 skinny edge prisms of volume x times dx squared and 1 tiny cube of volume dx cubed in the corner. Hence, the total change in volume is 3x squared dx plus some smaller terms involving dx squared and dx cubed. Again, these smaller terms become negligible as dx shrinks. So all we are left with is 3x squared dx, and dividing by dx we obtain the derivative of x cubed is 3x squared. If you keep going, you'll realize that the result holds for hypercubes with powers of 4 or higher. So we can generalize from this pattern that the derivative of x to the power of n is n times x to the power n minus 1. We call this the power rule, and now you don't just have to trust this rule because it's written in your textbook, but because you have seen how it can be built using geometry. The interesting thing is that this holds not just for positive integral powers of x, but also when n is negative or a fraction. Let's look at 1 over x, for instance. We draw a rectangle whose base is x and whose height is 1 over x. The area is x times 1 over x, which is exactly 1. Again, we increase x slightly by a tiny amount dx. The rectangle changes shape, it becomes slightly wider but slightly shorter. The new area is still 1, but the individual dimensions have changed. Visually, we see 2 small strips, an orange one added to the right and a teal one lost from the top. If we balance these 2 changes and rearrange the equation, we arrive at a relation between dx and the change in 1 over x. The result, the derivative of 1 over x is negative 1 over x squared. This matches what we would expect if we extended the power rule to x to the power minus 1. We can further look at the square root of x. Once again, we have the plot of root x and a rectangle whose height changes as root x for the change in x. The total change in area can be written in 2 ways. First, we expand x plus dx and square root x plus d square root x and compute the new area algebraically. Then, we ignore the smaller second order term, the product of dx and d square root x, and keep only the two dominant contributions. Second, we apply the binomial approximation directly to x to the power of 3 halves and get the new area in terms of dx. You can watch my video on approximations in case you aren't familiar with how binomial approximations work. Coming back to the problem at hand, equating the two results gives us a clean expression for the derivative of square root x. And the answer? 1 divided by 2 times square root of x, or 1 half x to the power minus half. So once again, this is consistent with the power rule. So we have ascertained that the power rule works for integer powers, negative and positive alike, as well as fractional powers. How about the derivative of the exponential function e to the power x? Let's take a look at the graph and take it a step ahead. At every point, we draw a tangent and compute its slope. What we find is remarkable. The slope at any point is equal to the value of the function itself. If y equals e to the power x, then dy by dx is also e to the power x. In other words, e to the x is its own derivative, and this makes the exponential function so central in physics and mathematics, especially when dealing with growth, decay, feedback, and continuous compounding. Now for logarithms. The graph of y equals ln x grows slowly but steadily. Its slope gets smaller as x increases. When we compute the tangent at any point, trace the derivative curve formed by it, and compare it with the value of x, we find that the slope is exactly 1 divided by x. If you think about it, this aligns perfectly with the inverse relationship between logarithmic and exponential functions. If it's not clear how that's the case, maybe you can try to see it for yourself in a while, once we have covered the chain rule. Now how about trigonometric functions? Here's the sine curve. Watch what happens as we trace the tangent at each point. After a while, you notice that this traced path exactly follows the shape of the cosine curve, which means the derivative of sine x with respect to x is cos x. As an exercise, you can try and construct a geometric proof for the same using a unit circle and see how sine theta changes for a tiny change theta. There's a pretty visualization of the same on 3 Blue 1 Brown's video on calculus, and I'd greatly recommend you to check it out. Now, in a similar fashion, if we plot the derivative of cos x by tracing the path curved by the slope of the tangent line, we see it's the inverted plot of sine x. Thus, the derivative of cos x is minus sine x, and that is our result. So now we can finally summarize all the key results we have seen so far, from the power rule and exponentials to logarithms and trigonometric functions. These results are worth internalizing as they show up all across physics, from oscillations and waves to radioactive decay and entropy and much more. With this foundation in place, we can now truly appreciate how all of this plays into physics with a striking example, the interference of two radial waves. Imagine two circular waves propagating outwards from a point. Their crests and troughs constantly overlap, building a complex ripple pattern. In 3 dimensions, isn't it beautiful to look at? A breathtaking patchwork of color shifting across space? To understand this mathematically, we write the wave as a superposition, and you can see the equation written on the screen. Using trigonometric identities, we can simplify this into a product of two functions, one representing the high-frequency oscillations called the carrier wave, and the other an envelope that modulates it. Of course, we'll cover these things in further detail when we study about waves, so do not fret if you do not completely understand what's going on here. Just try to understand how derivatives play in. Now, the envelope term governs the shape and the speed of the ripples, and we can use our newfound knowledge of calculus to find out how fast this envelope travels, that is, how fast the regions of constructive interference move. And what we do is simply differentiate the phase of the envelope with respect to time, and that gives us the group velocity, a foundational result in wave physics, whether you're studying radio signals or optical pulses. As yet another straightforward example, let's take on the ball thrown into air once again. We can now find the slope using some of the results that we saw earlier. The height is given as v0t minus half gt squared, and differentiating this gives us the velocity as v0 minus gt, where v0 is of course the initial velocity with which the ball is thrown upwards. Now differentiating this one more time gives us the acceleration as minus g. Hence, just from the position graph, we have obtained both velocity and acceleration purely through the lens of calculus. The curve thus becomes a gold mine of physical meaning, with derivatives helping us read the motion from the shape. Now, often in physics, we are going to encounter functions that are, in a way, combination of other functions. So, it becomes crucial to know how to deal with them. Consider this classic spring mass system undergoing damped oscillations. The mass is initially displaced from equilibrium, and as it moves, its amplitude decays over time due to damping. We'll observe this system both physically and mathematically. The analytical expression for its position as a function of time is a product of two terms, an exponentially decaying envelope and an oscillatory cosine term. Over time, the mass oscillates back and forth, but the amplitude steadily decreases due to the exponential decay. We can see how this function behaves over time by plotting out its graph, and this shows a damped waveform of oscillations shrinking in amplitude as time progresses. How would you find the velocity of this mass? Of course, you're right. You would be familiar by now. We differentiate x of t. But since x of t is a product of two functions, we need to use something that we call the product rule. Let's build some intuition. Imagine the position function as the area of a rectangle. One side represents the decay term and the other represents the oscillating cosine. If both sides change slightly due to a small time increment dt, the total change in area df can be decomposed into three parts: the change due to the vertical growth or oscillation, the change due to the horizontal growth or decay, and a tiny corner region that comes from the product of both differentials. These changes correspond to the differential form of the product rule. Now, by dividing by dt, we get the derivative. And you can see the result written here, and thus this is how the product rule works. Simply put, if we have a product of two general functions, f of x and g of x, the derivative of the product is f prime of x times g of x plus f of x times g prime of x. And while we are at it, we can take a quick look at the quotient rule too. I'll leave it up to you to derive that from the product rule. Simply put in the reciprocal of g of x in place of gx into the product rule, and you should get a matching result as the equation on the screen. Now sometimes we would need to take a step further when we are dealing with a function nested inside a function, and that is where the chain rule comes in. Say we have a simple pendulum and we want to find the horizontal velocity of the bob as it swings. The displacement in the horizontal direction is given by x of t equals L sine theta of t. Here theta of t is the angular displacement, which itself depends on time. So we see that x, in a sense, is a function of theta, which in turn is a function of time. To find v of t, we differentiate and find dx over dt as L times d over dt sine theta t. So what we essentially do is we do a chain of differentiation. We first differentiate the function of x with respect to theta, and then we differentiate theta with respect to t. And then we multiply those together, so we end up with dx over d theta times d theta over dt, which eventually gives us L times cos theta of t times d theta dt. What we used here is called the chain rule, and I think you can appreciate why it's called so. Putting it in plain mathematical language, the derivative of a composition f of g of t is f prime g of t times g prime of t. A fundamental tool when the input function itself varies depending on some other factors. Now, using this chain rule, we can derive some other derivative identities that come up quite frequently in physics and mathematics. So I'm putting in the identities here, but I leave it to you as a task to derive these on paper. It's handy to remember them, but if you're having trouble memorizing, remember it's fine. You'll soon become very familiar with them over the course of time through solving problems after problems. Now, so far, we have seen many ways in which derivatives are useful, mostly when discussing rate of change. But there's yet another use for them when we need to find extrema. For instance, imagine launching a projectile at an angle theta with fixed initial speed v0. The horizontal range r depends on the angle, and this is given by v0 squared by g times sine of 2 theta. Now say we want to find the angle at which the projectile travels the maximum horizontal distance. To find this, we would need to set the derivative dr by d theta as 0. Why? Because at a maximum or minimum, the slope of the curve is 0 as the tangent changes directions here from positive to negative or the other way round. So in this example, we would get that theta should be pi by 4 radians or 45 degrees. Physically, you can hopefully see why this would give us the maximum range, but mathematically we still need to ascertain how we differentiate between maxima and minima. For now at least, you can agree that the point where the derivatives become 0 is a candidate for an extremum, and it is known as a critical point. Now let's take another example. This time, consider the potential energy stored in an ideal spring. It's given as u of x equals half kx squared. If we plot this, we get an upward facing parabola. Now it makes sense to assume that the spring has no external force acting on it when the spring is relaxed, which from the graph we see is where x is 0. We confirm this by differentiation that du over dx, which is kx, is indeed 0 when x is 0. At this point, the spring is at its equilibrium and the potential energy is minimized, and the force thus, which is minus du over dx, is 0. So now we can go back and address the important question. How can we tell whether a critical point is a minimum or a maximum? For this, we need to use what is called the second derivative test. If the second derivative at a point C is positive, that is, if double prime of C is greater than 0, then the function is concave upward at that point and we have a local minimum. And if f double prime of C is less than 0, then the function is concave downward and we get a local maximum. This test gives us a clear way to classify the nature of extrema without needing to graph the function. Again, in some functions, the graph may peak or dip at more than one point. In such cases, we have to deal with local and global extrema. A local maximum or minimum occurs in a small neighborhood, for instance, the peak of a hill or the dip of a valley. In contrast, a global maximum is the highest point over the interval a to b, and a global minimum is the lowest. To identify global extrema, we evaluate the function at all critical points within the interval as well as the endpoints. Thus, we have seen how differentiation allows us to locate and analyze extrema in a wide variety of real-world scenarios, all the way from optimizing trajectories to minimizing energy. There's actually so much more to explore in differential calculus, from L'Hopital's rule for evaluating indeterminate forms, or how extrema behave in multivariable functions. But for the most of the physics we'll be dealing with for now, that won't be relevant until we go into higher level courses. So for now, we have mastered the subject. In the next video, we shall be moving on into integral calculus and part ways from rates and slopes to areas and accumulation. If you found this helpful, consider subscribing to Eigen Academy to follow the rest of the series, and I'll see you in the next video. Bye.